everyone at least knows. Okay, cool. So as everyone at least knows the definition and basics of induction, so I'll just go through everything quickly in this segment. So induction itself is like very often classified into two types: weak and strong induction. So for this segment, we'll just first focus on weak induction. So what does weak induction state? Weak induction states that m is true. If n is true, then n plus 1 is true. Okay. So I guess I'll just. So it's 1, 1, and you have 2. And you have that both 1 and 2 are 1 and 2 are true. Then you have that for all natural numbers greater than m, or if m was negative for all integers greater than m, you have that the statement is true. Okay. So how does this work in relation with well ordering principle? So are you guys familiar with well ordering principle? That was covered, I think, a class or two before.
Yes,
Do you guys
sir.
remember?
I think everyone knows.
What? Can you come again?
Yes, I know about oil ordering principle.
Okay, cool. So I'll assume that everyone at least has a basic idea because it was covered previously. So can someone state the well ordering principles statement? Preferably would recommend you guys to like say it so that I can write it without having to flip tabs.
We can arrange the positive integers and just say that a greater than equal to b or b greater than or equal to a or a equals to b. There should be an arrangement between which we can say.
Sure. Okay. Yes. What is after this? Just give me a second. I think my computer is slightly laggy. Arrange positive integers such that a less than b or less than b or a greater than b or a equal to b for all a comma b belonging to natural numbers. Okay. Another way that at least would be more useful in this case is that we basically have the least element definition, which is that for all subsets S of a positive of natural numbers, we have that we have just note S not equal to the empty subset. We have a least element in S. Okay. Did you guys study this form of well ordering principle?
Yeah, there'll always be a least element in every, I guess, non-empty subset.
Yeah, so every non-empty subset has a least element. Okay, cool. So can someone tell me why this is equivalent to weak induction? Does anyone know the proof? Why this statement is equivalent to what weak induction states? Okay, so I guess one way to think about this is that let's consider a set S of numbers. For this, let's actually replace, let me just replace M with 1. Oh yeah, so 1 is true, and if n is true, n plus 1 is true. S of numbers such that we have a least element S. We have a set S such that statement isn't true for small s belonging to capital S. Okay. Okay, my computer's like missing stroke, but okay, cool. So let's consider this set S of numbers. Okay. So we have that one is true. Okay, so one does not belong to capital S. And assuming that capital S is non-empty, we have that, assuming capital S is non-empty, we have that it has a minimal element k, which implies that k minus 1 is a natural number not in S. K minus 1, k belongs to natural numbers. Okay, k minus 1, k minus 1 belongs to natural numbers because k is not 1, because 1 is already true. Okay, and k minus 1, so k minus 1 belongs to natural numbers. Thus, we have that, but by this, n belongs to natural numbers. So this implies that k minus 1 is true, which implies that k is true, which means that a minimal element k, so that implies that k does not belong to S. Okay, which implies that the set S of numbers for which the statement isn't true must be the empty subset. Does this make sense? This is a proof of induction and how it's equivalent to, or how it can be proved by a well-ordering principle.
No,
You
actually, I
can
didn't
prove.
get that. Well,
Okay,
empty
so
subset part.
yeah, cool. So we have that S of numbers for which the statement isn't true, right? So we have some induction statement, and we have the following two properties about the induction statement. One is true, that is that for n equal to 1 is true. And if n is true for, then n plus 1 is also true. So if it's true for n, then it's true for n plus 1. Okay, so let's assume that it's not true for every natural number then, right? So that means that there is going to be some non-empty subset S of natural numbers for which the statement isn't true. Does this make sense?
Yes.
Okay, I see. You're gonna prove that this, this S dash, it's empty.
Yeah, so what we want to just show is that S is empty, S being the set of all such numbers for which the statement isn't true. So we know this property that it must have a minimal element by well-ordering principle, since it's a subset of natural numbers. But we have that k minus 1 does not belong to S by minimality of k minus 1, and k minus 1 belongs to n as k itself is not 1. Okay, and we have that it's not 1 because we have 1 is true. So it satisfies two properties. And this implies that this statement holds for k minus 1, which means that k is true. So it cannot have had a minimal element. Does this make sense?
Yeah.
Good. Okay, so that's just a very brief intro to what exactly is induction. So I guess we can do a really easy example of induction too. Show that via induction, you all are probably familiar, but summation of the first n numbers is n into n plus 1 by 2. So you have the trick with the summation that you can do. So I guess that's a proof without induction. So 1 plus 2 dot 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 until n, if this is equal to s. If this is equal to s, you have that n plus n minus 1 dot 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 until 1 is equal to s. So this is the proof without induction. Or you have that, which implies that 2s is equal to n times n plus 1. This is because each of these pair up to n plus 1 and there are n such values, which gives s is this. So this is the proof without induction. So can you all try to come up with a proof with induction?
So basically, we're gonna first assume for it's true for the value k, and then prove that for value k plus one, the equation also holds, and the base cases
Sure.
obviously hold, like for one and two.
Yeah. So let's just do base case. So base case. 1 into 2 by 2 equal to 1, which is equal to 1 plus, yeah, it's just 1. Just 1, which is equal to 1. So that's true. So step. So we have that summation of I equal to 1 till k, 1 till k, I is equal to k times k plus 1 by 2. And we have that summation I until k plus 1 will be equal to k into k plus 1 by 2 plus k plus 1. So we have that. We have that. Yeah, so we have that this is equal to k plus 2 times k plus 1 by 2 as desired. So this is the induction step. So that's base case, and this is induction step. Does this make sense?
Yes.
Okay, good. Everyone's clear?
Yeah.
So now we'll go to the first first question that's slightly tricky. Okay, so we'll be doing, so what we did here is, um, so here we had an induction with a single base case. So we'll basically be doing something very, very similar, but this time what I want you to do is like this. So if, okay, so I'll just first explain the question. You want to basically show that every number k can be expressed of the form k is equal to plus or minus 1 square plus or minus 2 square until plus or minus n square for some n. N is your choice, but you want to show that every number k can be expressed of this form. So assuming that k k can be expressed, k can be expressed. Okay, this is some sort of induction type, because it's not very frequent that a direct induction question comes in an Olympiad level scenario. So usually there'll be some sort of trick attached to it. So this is one very common example that happens. So assume that k can be expressed. Assume k can be expressed. Can you show k plus 4 can be expressed? K plus 4 can be expressed as above. Okay, so that is that for some sequence of plus or minuses, and for some n. These plus or minuses and n is entirely up to you. You have that k can be expressed as this, as some sort of continuous sum. And the question is, can you show that k plus 4 can be expressed in such a sum? Okay. So I guess a very nice thing to note here is these are quadratic in terms of like some value, and you'd probably want to add some consecutive string, and this is just some constant value that we want to add. So some sort of manipulation with the plus or minuses with the quadratics. So if I had that k is equal to some sequence like this, it'd be nice to see that n plus 1 squared plus or minus until some n plus t squared is equal to 4. So this would be some very specific sequence of plus or minuses. Okay. So does anyone have any ideas on what might be a good t and a good sequence of plus or minuses?
I think I have a particular string of numbers n plus 1 squared minus n plus 2 squared minus n plus 3 squared plus n plus 4 squared.
Okay, so that's basically, yeah, so that's correct. Uh, so here it's just n plus 4. So, so this is just also. So yeah, that's correct. So you got minus n plus 2 squared minus n plus 3 squared. Is my handwriting legible, by the way? Is it
Yes.
kind of? Okay, cool. Because I've been informed multiple times my handwriting isn't excellent, and I completely agree with whoever said that. And like today, the writing isn't also great. I think my computer's slightly laggy. So the idea is n plus 1 square minus n plus 2 square minus n plus 3 square plus n plus 4 square is equal to 4. You can prove this by just expanding it out. So k can be expressed, then k plus 4 can be expressed by just adding n plus 1 square minus n plus 3 square minus minus n plus 2 square minus n plus 3 square plus n plus 4 square, because this thing just sums up to 4. Okay, so now all that's left to show is in fact just that 1, 2, 3, and 4 are expressible. So I'll leave that as a pretty easy exercise for all of you. Shouldn't be too difficult. You guys can try that out. Won't take too long. But we'll move on to the other type of induction that you pretty frequently see. This one's called strong induction. So the previous one's called weak induction. This one's called strong induction. So the question is, what does it mean, right? So first of all, what is strong induction? By the way, people who have seen the question, just like send me a message. Just also quickly just want to verify everyone's clear with the proof for problem 1, right? That's the plus or minus question. This one. So you should be able to like vote whether you guys are clear on the problem or not. Yeah, because like if anyone has a doubt, I can like explain or like help out with any part.
I've got a question like, why did we choose 4? Couldn't we have chosen like almost like anything, perhaps? Anything meaning anything that we obtain
Okay.
operating to terms.
Okay. So you can. Okay, so you can actually choose just about anything. So the motivation for 4 here is actually, I'd say, kind of natural. The idea here is like this. Okay, so can you show that if you wanted to get some form of constant term from quadratic of, well, n plus 1 to n plus t square, the number of terms have to be a multiple of 4. Number of terms is a multiple of 4. You can show this by showing that n square coefficient has to be balanced out by plus or minuses. So that will take an even number of n's. And you can then balance out the linear coefficients and then show that between all the positive n squares, there should be an even number of them. Hence, you have like a net total of a multiple of 4. So that motivates choosing 4 numbers. And when you take 4 numbers, especially the first consecutive 4 numbers, n plus 1, n plus 2, n plus 3, and n plus 4 square, and you alternate them in a plus or minus format, you end up with 4, which is what motivates the 4. So you can actually, in fact, a very simple extension is that you just add n plus 5. So plus n plus 5 minus n plus 6 minus n plus 7 plus n plus 8. Basically repeat this until n plus 8. 8 squared plus, and you got minus and minus. Then that will be just equal to 8 because that's just 4 plus 4. So you can, but the only issue there is that you will now have additional case. You'll have to prove the base cases 1 until 8, and then you can proceed. So that is why you pick 4, because it's going to be the smallest out of, at least with like 4 length sequences of n's. So yeah, you can, I'm not fully certain if you can get some sort of sequence that ends up mapping to 2 or 3 perhaps, 2 probably. Yeah, but I'm not fully certain on that. The reason for 4 is because this is the shortest that you can get, and that maps to 4. And showing small cases is not very difficult. The base cases are easy. Does that explain the motivation?
Yeah, follow.
Good. My computer's acting weird today. Good. Okay, so we'll go on to strong induction. I think everyone else was clear. So that was, yeah, it was 15. Yes. Okay, good. So what is strong induction, right? So what strong induction states is, so previously with weak induction, what we had is that n is true implies n plus 1 is true. This is weak. Okay. So what strong induction states is that strong is 1, 2 until n is true implies n plus 1 is true. This is strong. Okay, so a very frequent application that you're going to see using this is called the fundamental theorem of arithmetic. So probably most of you are familiar with this already, but it's that any number can be expressed as a product of primes. So 6 is equal to 2 into 3. 12 is equal to 2 into 3. And yeah, so any number that you give. So for example, 5 is equal to 5 because that's a prime by itself. So you have that every number can be expressed as a product of primes. Yeah. So the question is, how do we prove this, or how does somebody prove this? Right. So for this, we use strong induction. So can all of you try? I guess I'll give like 5 minutes. Some of you might be familiar. Wait. In the meantime, for those of you who are like probably like bored because you've done like this other stuff, all of you have understood the problem, right? The fundamental theorem for arithmetic one.
Yes, sir.
Okay. Also, don't call me sir. Like, no, don't. Yeah, you just feel free to like just say yes, or like you can just call me Nanda. That works. For those of you who have done like this level of stuff, you all can try this problem. This one's not easy. So only do this like if you're like confident in your ability with induction. Is it readable? You guys can take a screenshot. This is for people who are marking can solve IMOP3s. It's not that difficult. It's at par with an INMO question, but yeah, it's not easy. I would say. I'm assuming you've taken a screenshot. If you need me to go back, just send a message or like you can speak up. Yeah. So this will be that we're working on in class at least. This one, a fundamental theorem of arithmetic. The other ones, if you're bored of class at the moment.
Can you show that one once again?
Sure. Take a quick screenshot. If any of it is not legible, I can send the source of the problem.
Okay, done.
Do you have permission to send images in chat? If you do, you can like just share it in case someone wants it.
Yeah, people do have permission to send in private chat.
Okay,
On Zoom
cool.
you're
That
asking,
works.
right? Yeah.
Yeah, on Zoom, on Zoom. Let me know if those of you are trying like a fundamental theorem of arithmetic have gotten approved for it.
Sir, I think I have brought up two, but not sure.
Yeah, that's fine. We can work it out. So what's the proof? Oh, it'd be nice if I just move down first.
I first assumed that we can do it for like 1 to n,
Okay.
and we can show generally that 2 or 3 works.
Okay. For 1 to n, 1 to n. Okay, so assume for 1 to n it's true. It's true. So what you want to do is we want to show it for n plus 1.
Yes.
Okay, so we'll deal with base cases later. I think they're quite trivial in this problem.
So there are two cases for which n plus 1 is prime or n plus 1 isn't prime.
Yeah, that's good. So let's deal with the case n plus 1 is prime, mainly because it's shorter. Okay, so what happens if n plus 1 is prime?
Because n plus 1 is prime, so we can write n plus 1 as n plus 1 because like
Yes,
it's
so that's a product of prime, so it's just n plus 1. Or if you want, you can write it as n plus 1 times prime, where 1 is not a prime, but we're just expressing that we're writing this as the product. Okay, so okay, so this just clears off when n plus 1 is prime. So we have case 2, n plus 1 is equal to d1 times d2, d1 greater than d2 greater than 1.
we can
Yeah.
see that d1 d2 both are less than or equal to n, because if not, then one of them should be n plus 1, and that means d2 is equal to 1, so that's contradiction. So d1 and d2 belongs to n, and we can write d1 d2 as product of primes.
Yeah, so we can express d1 is equal to p1 to the power e1 dot dot dot, and d2 is equal to q1 to the power e1 dot dot dot, and n plus 1 is just p1 to the power e1 till t whatever to the power u that. times q1 to the power e1, uh, or let's just call it f1. Don't want to use variables. So q1 to the power f1 and so on. So that's a product of primes. In case any pi is equal to qj, then we just merge the coefficients together, like the powers together. So this is how you express, well, any natural number as a product of primes. Is this clear? So this is something
Yes.
that if any of you are more inclined towards number theory than um, combinatorics, you guys are going to deal with this quite frequently. But one of the easiest proofs for this is in fact combinatorial in nature or via induction. Yeah, that's nice. It goes to show how like various things can merge, so number theory and combi. Okay, so we have a personal favorite question of mine. It's something that I saw like really early into my Olympiad prep. It's a fairly nice question. Okay, so here's the question. So you have, okay, so you have a board. Okay. So are you guys familiar with what a Tromino is? It's this. It's like an L-shaped three square tile. Okay, so it's this shape, and you have a board. Okay, so you assume that for now it's a 2x2 board. Okay, so this is how you'd place a Tromino on it. Okay, so does a Tromino make sense to everyone? It's like a domino, but with 3 pieces instead of 2.
Yes.
Okay, cool. So here's the question. Okay, so you are given a board of size 2 to the power n. Okay, that means that it's a square grid and it's got side length of 2 to the power n, 2 to the power n. So this is the case where n is equal to 2. This is n equal to 1. So this is n equal to 1. And this is n equal to 2. Okay, your job is to come up with a tiling such that, so, or if you want flavor text, yeah. So uh, give me names, guys. Like, give me names. So you want 2 players. Preferably not Alice and Bob because that
I was going to say Alison.
would be the original. that would be the original problem wording. So we don't go with Alice and Bob because we'll be in ego
Vikram and
over here.
Betal. Vikram and Betal.
Ram and Shyam. Okay, fine. Vikram and Beetle. Where did Vikram and Beetle come from? That's a very interesting.
Oh, Vikram and Betal, like in more problem.
Yeah, no. I got that, but do you know where they got their name things from? Like where they decided those names from, or was that?
Oh, I don't know that.
Uh, so Vikram and Betel. So Betel places a bomb on one of the tiles. So say Vikram wants to place trominos such that every tile is covered by exactly one tromino except the tile with the bomb. This one? Yeah. Every tile, yeah. So every tile has a bomb on it. Yeah. And the bomb can be anywhere in the tiling. And both Vikram and Beetle know where the bomb is. So Beetle places the bomb, and Vikram just wants to tile every other square other than that. Can Vikram ensure he can do this? Or
Yes.
prove that Vikram can always do this? I guess with how I've been going with induction, it's quite clear that Vikram can do it. The only question is how. That's actually nice. I've never learned the folklore behind Vikram and Beetle. That's interesting. Thanks. Cool. So for example, for 2 to the power n, an example domino tiling will be this. In fact, this should hopefully give you guys ideas on how exactly to go about the problem. Hopefully it's like clear. The grid lines at the background, we'll just assume that to be the actual grid. So this is the tile with the bomb on it, and this is from, I should probably use like colors. A second. So we have Tromino 1, Tromino 2, Tromino 3, Tromino 4, and Tromino 5. Okay, so these 5 cells, these 3 cells will be covered, these 3 cells will be covered, these 3 cells will be covered, and these 3, and these 3. And thus every square except the one with the bomb in it is covered. Have you guys seen this problem before? Because I think this problem was quite
Yeah,
famous.
seen
The
it.
one that I'm. Huh?
I've seen it somewhere.
It's the first problem of mathematical circles, I guess, in the chapter
Really?
introduction.
I've never done mathematical circles. I've not seen the problem. Yeah, but like this one, I just liked it. It's a nice induction question. How many of you have already done this problem before? Because if lots of people have done the problem before, then I don't want to spend too much time. Yeah, okay. Uh, sure, I'll write it formally. Okay. Uh, with the part. I'm not misspelling stuff, right? Or is it double T? And then single T, fine. Places a bomb on, on one of the cells. Trominos. Does the question statement make sense? What do you mean by just two Trominos? L Trominos. L as in L refers to the shape, not that's bad handwriting. I'm so sorry. With L, this is the so an L Tromino refers to Trominos specifically of this shape, uh, as opposed to so formally Trominos also include these ones because Tromino is like domino but like 3 squares instead of 2. So this one specifically called the L Tromino because it has the L shape, and this one's the line Tromino. So regarding what argument you want to go for, I would prefer that in class at least we're discussing induction based arguments, but like if you have other arguments, just like message me. I'll read it and I'll like let you know if that's correct or anything. So a couple of people have messaged that. So yeah, feel free to like message any argument. And if you have an induction argument, you can like go ahead, like mention it to the class as well. I don't plan on doing this question, but like so I'll let people think about it till like 7:50 IST, and then we're going to discuss. So if you have like an induction argument, you can like speak up now itself. For non-induction or non-combinatorial arguments, even feel free to like just send me a message. I'll definitely go through it. Uh, so one really easy thing to note is that if n is divisible by 3, you cannot do this. It's not n odd. I'm not really certain what n odd. 5. I'll let you know what n odd, but n divisible by 3 you cannot. Uh, Main reason for that is
2 to the power.
there's a bit of what?
Sir, I am saying 2 to the power n plus 1 minus 1. In that case, shouldn't be divisible by 3.
2 to the power. Wait. Can you repeat? 2 to the power n plus 1. What were you saying?
Minus 1
Minus 1.
uh, shouldn't be divisible by 3.
Yeah, so if this is not why should this can be divisible by 3? The point is the square. So when you're dealing with the square, that's 2 to the power 2 and
2n.
minus 1. So this will always be divisible by 3. Uh, in
Oh
fact, this
yeah,
is just because it's 4 to
I
the
wanted to say
power
2 to
n
the power
minus 1.
2n actually.
Yeah, so this is just, it's going to be like 4 to the power n minus 1, which is 3 times something. So that will be always divisible by 3. But for example, if it was 3k, right? So this is, I think someone messaged in chat saying that if you put odd numbers, it won't work. So I'm not fully certain what odd numbers, but for multiples of 3, it'll be 3k square minus 1, which will be minus 1 mod 3. So won't be divisible. Uh, yeah. Uh, Sharnya, your solution's correct. You want to explain in class? Yeah. That's exactly the same as the intended solution. So you can go ahead.
So first we'll assume for k this is true, like there will always be like one vacant grid, and then we're gonna prove for to the k plus one if this holds or not. So basically, a 2 to the k plus 1 grid can be divided into exactly 4 2 to the k grids, and we know from a previous statement, assumed statement, that there will be one vacant grid. So there are a total of 4 vacant grids, and we can arrange those grids to the center, and so we can place a Tromino, L Tromino in that, and we'll be left with one vacant grid.
Yeah. So for example, if the bomb was in this, so we divided it over 4 different segments. So if the bomb was placed in some arbitrary spot in this grid, then all you have to do is that you cover up. So you leave an open space at the bottom left corner of the top right grid, the top left corner of the bottom right grid, and the top right corner of the bottom left grid. And we're assuming that the bomb is in the top left. So if the bomb was in the top right, you would basically have the Tromino here, and you would have that this is not a vacant spot. And in this grid, we can pick any arbitrary vacant spot. So we'll pick that vacant spot as the one with the bomb. And we can place an additional Tromino here. And in fact, that's all there is to the problem. Does the idea make sense? Uh, I've mentioned that square grid of size 2 to the power n. So it's fine even if it's in odd or anything, because we're only worried about okay, I guess slightly to note n greater than equal to 1. But yeah, besides that, I don't Okay, does whatever I said about 2 to the power k plus 1 make sense to people? About how you get it from 2 to the power k. So what we're doing is we're inducting on the power here because that is the free variable. So what we're basically doing is that we're moving from 2 to the power k plus 1 to 2 to the power k.
Yes,
Moving from
could
2
you
to the power
repeat?
k to 2 to the power k.
Could you repeat
Yeah, okay.
the induction process?
Yeah, sure. So okay, so does it make sense if I say that the 2 to the power k plus 1 grid can be divided into 4 grids, each of size 2 to the power k?
Yes.
Okay, and the bomb is going to lie in exactly one of these grids, right?
Yes. Right.
So without
Understood.
loss of generality, I'm just going to assume that the grid is the top left grid. Otherwise, I'll just rotate the entire thing by how much ever is the angle such that it lies in the top left grid. Okay, and what I do is for the top right grid, I can I tile it however I want it, such that I have the ability to choose. So what Vikram does is that he assumes that in this top right grid that there's a bomb placed in the bottom left square. He just assumes that there's a bomb, and he tiles the remaining squares in such a manner. So that basically means that all of the squares except the bottom left square of the top right grid is covered. So this square is empty. He does a similar thing here where he pretends the top left corner of the bottom right grid has a bomb. So everything else except the top left corner is tiled. And he does the same with the bottom left where he assumes that the top right corner has a bomb. So he's got these three squares that are empty, and he's got these three grids that are entirely tiled. And for the 2 to the power k grid, which contains the bomb, he assumes that the square that has the bomb, and he tiles all the remaining squares. So the bomb need not be right next to the Tromino. In fact, the bomb could be like anywhere. Uh, oh, that's highlighter. Cool. So in fact, the bomb could be anywhere. Like it could be in the middle. That's fine. He just ensures that everything else except that is tiled. And for the three tiles that he's picked in this manner, from one from each of the three grids without the bomb, he places a Tromino over it. So regardless of where the bomb is, he manages to cover all the remaining tiles except the bomb. Does this make sense?
Yeah.
Is everyone clear with this? I'll just because this one's slightly more trickier, I'd say. So I'll just feel free. I've just made another poll, so you guys can just share if you're fine. Because this one's a nice question to always do. So if you have like any doubts, let me know because it's important that you're clear with this. We have time for this. Uh, who has the doubt? I can clarify.
Can you repeat the solution?
Yeah, sure. Okay. So imagine that you're Beetle, right? So you've placed the bomb somewhere on the grid, right? So as Vikram, I basically split the 2 to the power k plus 1 grid into 4 grids of size 2 to the power k. So each of these are 2 to the power k long. Okay.
Yeah,
Does it
yeah.
make sense that I have 4 of these? Now in each of these grids, I can like just pretend that there's so, and I'm just rotating it so that the bomb is on the top left grid. Okay. Does this make sense? Out of the 4, the bomb is on the top left grid. Does that make sense? Because if it was on the top right grid, I'll just sort of like rotate the entire grid by 90 degrees anti-clockwise. Does this make sense?
Yeah, yeah.
Good. Now, what I do for the top right grid is I'll assume that where the bomb is there, I don't want to place a Tromino on top of it. And I have tilings everywhere else within that 2 to the power k grid. For the other three grids, I'll assume that this block. So for the top right grid, that's the bottom left block. For the bottom right grid, that's the top left. And for the bottom left, that's the top right. These three blocks within each of these grids have a bomb. So by my assumption that I can tile it excluding one position for the bomb, I have that this position, so I can leave this position empty and the rest of the grid is tiled. This position's left empty and the rest of the grid is tiled. This position's left empty and the rest of the grid is tiled. And these three form a Tromino shape. So I can just simply place a Tromino on top of this. Does this make sense? Aritra? Okay, is this clear?
I am now thinking about this.
Okay. Yeah, you can take your time. It's not an easy problem. It's a nice problem. I personally really, I guess it gives a good intuition
It
about
is a
how
good problem.
induction works. Yeah. This was slightly. Okay, so I'll do the combinatorial games slightly later if we have the time. But there's another really important question that I wanted to do. This one has a very long problem statement, so I wasn't writing that one. So this is the problem. Okay, so this one's more or less about. This one's going to focus more about using multiple variables during induction. So here you have two variables, n and k, and you have. So you feel free to read the problem statement, but you basically have. So you have some n circle. Oh God, that's a horrible circle. You have n circles on the plane, such that all of them are pairwise intersecting, and no point is on lies on three circles. So that's basically saying that all of the circles intersect, and all of the intersection points are distinct. Yeah, pairwise distinct. Yeah. Uh, yeah. These circles have a point in common. Okay, and you want to color each of these intersection points. So let your circles be named C1, C2 until Cn. So here n is 3. And you have colors 1, 2, and 3. Or, okay, give me colors. We can go with 1, 2, 3, but for like the base case, we can use colors of your choice.
Red, blue, green.
What? Wait. Yeah, just say the colors. Feel free to like go crazy. If you guys want to use amber, that's fine.
Just Vipgeo should be fine, like all the colors are green.
Your voice is slightly breaking. Can you like send it as like a text message? My internet. You guys can hear me fine, right? That's what my internet's.
Yes, you are audible clearly.
Fine. Oh, WebGR. Oh, okay. So, well, I mean, we have three colors. So I'm not sure if we can put the entire violet, indigo. We can go with like violet. Or, instead of green and blue, we just go with something like cyan and orange. Yeah. Orange, cyan. Yeah. My writing part's being weird. Yeah. Okay. So we have violet, cyan, and orange as our three colors. So you can just color them how you like. So for example, you could just do violet, violet, cyan, cyan, and orange and orange. Okay. So each intersection point is colored with one of the three distinct colors, and every color is used at least once. So here every color is used twice. and exactly k distinct colors occur on each circle. So if you look at C1, the only colors to occur on. Did I mess this up? Oops, I messed this up. The coloring is bad. Yeah, okay, so this one's fine. This one is cyan, this one is cyan, this one is orange, this one's orange. So if you look at it, C1 has violet, cyan, so it has only two. C2 has violet, orange, so it does not have cyan, so it has two. And C3 has cyan, orange, so it has two. So this basically shows that k comma n, so 2 comma 3 is valid as n and k. So you want to find all values of n greater than equal to 2 and k for which such a coloring is possible. Okay, that's interesting sort of claim that it's related with Ramsey number. I'd say Ramsey numbers is complicated. There is no benefit whatsoever knowing Ramsey numbers for this problem. I don't. In fact, this one has a very nice closed form, whereas if you could find a closed form for Ramsey numbers, you would be hailed as one of the greatest mathematicians.
No, I am trying to say that the problem statement is kind of like Ramsey's number, not the solution. Like coloring in comma k pairs and like that.
Sure. Yeah, I'd say perhaps. I think there are graph theory solutions for. I'm not fully certain, but I think there might be graph theory solutions for this one. But they are more or less not. At least I wouldn't say that they're easy compared to the inductor solution. I think the inductor solution is nice, really clean, but it's definitely tricky. So one of the ideas. So I won't go too much into the base cases. The base cases themselves are also slightly tricky. So you can try that yourself. But I think one very important thing is going to be this type of induction. So instead of inducting from k to k plus 1, so for the pair k comma n, can you show that k comma n works? The pair k plus 1 comma n plus 1 works. There's a slight additional constraint here. So we have numbered our circles C1 to Cn, and we'll assume for the sake of not so pretty colors that our colors are named 1 to n. You have that Ci has color I on it. Yeah, Ci has color I on it.
What does
This one's so your circles are C1 to Cn.
Okay.
And your colors are 1 to n. So I guess it's very clear that k cannot be 0, so it makes sense to make this sort of statement. So you will have, so basically the thing about this is you have this nice sort of additional constraint that will let you perhaps make your coloring really easy. But along with this constraint, that means that when you're doing the induction step, your n plus 1 circle that you've just added better have the color n plus 1 on it. Okay, so it'll turn out that that's not too difficult. But this is a nice question to deal with. Does this involve principal inclusion exclusion? No, it doesn't involve principal inclusion exclusion. It's actually a very nice construction combi sort of thing. Yeah, but the only really smart stuff here are very personally the base case construction is tricky. I personally like that bit. If we have time, we'll actually discuss that as well. But we might be slightly low on time. The other thing that's involved is, well, the induction step. So this sort of induction step doesn't occur very frequently, but whenever it occurs, it usually is like a really sort of smart thing to notice, and spotting this like almost instantly makes the problem like it solves like 3/4 of the difficulty of the problem, I'd say. Like just spotting that such an induction step works. So just give me a also feel free to interact. This one's a slightly more difficult problem, so it would be nice if all of you like discuss and throw around ideas. So feel free to like say what all ideas you guys are working on as well. Sorry if I like take a while to reply to messages that you guys are sending as private messages. A few of you are messaging me, so like I'm trying to like clear them one message by one message. Okay, so can one of you at least tell me what do you think would be the highest value of k that highest value that k can take?
It should be n.
Okay, sure. So k is obviously less than equal to n. This is because there are only uh, n distinct colors. Uh, can k equal to n always be attained?
Yes.
Okay, so do you have a construction? Um, yeah. Can you show that k equal to n can always be attained?
I don't have a particular construction in mind.
Okay, okay. So you guys are just guessing that k equal to n can be attained. So I think,
Yes, it
although
seems.
yes, so that's a very nice sort of intuitive step towards working towards it, because well, the question asks for bounds, right? So it might be nice to form some sort of idea in your head that, well, what probably works. So a good thing about such questions is that usually, uh, if it's common in Olympiad, the solution set is most likely not going to look terrible, and if it looked terrible, it would be in a class. Okay, so you can assume that the solution set looks nice. So if k equals to n works, then good odds are that it's probably going to be some sort of k greater than something less than equal to n. So a good idea to work with here is n possible.
For
That is
n,
k equal to.
you could probably just color the pair of intersection points with every other ci as one of the n colors, and then notice that for the other set pair of points, you could color them with the other n minus one colors. Trivial.
Uh, I don't follow. Wait, let can you explain what you said with the three circles case?
Yeah.
So you
So
draw
if you
three
yeah.
circles.
So
Okay,
if you
so
could
let's call these
label them
intersection
as
points
yeah, 1, 2, 3.
4. I'm labeling the intersection points so that's easy for you to tell me.
Yeah, yeah,
You
sure.
can so 1 and 2 is
So
between. Yeah.
So for C1 and C2, the pair of intersection points I'm talking about is 3 and 4. So color them with any one of
Yeah.
like suppose red, blue, or green, any red, blue, or green.
Yeah. So
Yeah.
let's just say that this is R. So this have to be the same? So can I color this green?
Uh, I mean, three distinct colors, right? So you could color them as red as well. I mean,
Yeah. So like the question is, you want these? Do you want 3 and 4 to be the same color, or do you want them to be different
yeah,
colors?
yeah. I want them to be the same.
Sure.
Then
Mhm.
2, 1 could also work. C1 and C3 intersect at 2, 1. So color 2, 1 with a different color. Like maybe
So
green.
you want two to be colored green, and I'm assuming then you want one to be colored green as well.
Yeah. And so for
Now,
the same
wait,
thing,
wait. There's an issue here.
yeah.
So look at C1. Okay, so it has only four intersection points: 4, 2, 3, 1. These are colored red and red, green and green. We have trouble. There is no blue on the circle. We're working with k equal to n, by the way. So although
Okay,
whatever
okay.
you're
So
saying
I
will
thought
be a valid coloring for k equal to 2.
okay. We want to bound for k like a construction for k equal to n.
K equal to n, not k equal to
Okay, okay.
2.
So
Uh, I'll probably like nicen up the intersection points. I don't want C1 and C3 to intersect at 3 and 4. So I wanted to say bad. 2 and this is the 1. one's a slightly nicer. So C1 and C2 intersect at 1 and 2, C2 and C3 intersect at 3 and 4, and C1 and C3 intersect at 5 and 6. So the idea here is just asking you all to construct for k equal to n. We might be slightly low on time, so I'll probably try to that's pretty do you all want to try this for a bit longer, or do you guys want to start moving towards the solution for this problem?
For n equals 3, I have a construction, but I'm not able to generalize it further.
Okay. Yeah. No. Yeah. Sure. Let's go with the construction for n equals
Should
2.
I tell my
Yeah.
construction?
Yeah. Sure.
So
Yeah.
I have selected the colors red, blue, and green. So color 1 and 3 as red.
Okay. So one is red. So I'll just check this 2, 3, 4, 5, 6. So these two are red. Okay.
4 and 5 blue.
4, 5, blue.
And
3 and
2
6.
and 6 green. Yeah, so
Yeah. 2 and 6 green. Okay. So
it is
yeah,
quite a
this
possible.
works. This works. This works. So you all can verify, but circle one has 1, 2, and 6. 1, 2, and wait, sorry, 1, 2, and 5. 1, 2, and 5 on it. This circle has 1, 2, and 4, and this circle has it's this one 4 and 5 is sharing. So 6, 4, and 3 uh, of red, blue, green, red, blue, green, red, blue, green. Uh, so yeah, the generalization actually looks very similar to this. The idea is that so here, if you want to be basically replacing red, green, and blue as such. Uh, we'll be calling. So you had red here, right? So that's one. So it says you had one, and you had 1 and 3 had the same color, right?
Yes,
1 and
yes.
3 had the same color. So then we'll call this
Yeah.
color 2. Okay. This is called as 2. So I'll just mark this as CL2, CL2 for color 2. Then you had 4 and 5. So 4 and 5. So I'll mark this as CL3, CL3, and I'll mark this as CL1 and CL1. Okay. So the idea is that what's the intersection between circle 1 and circle 3? So that's going to be colored with 6, which is color 1, and with 5, which is color 3. Okay. Intersection between circle 1 and circle 2 is what is it? 2 and 1. So 1 is colored with color 2, 2 is colored with color 1. The intersection between circle 2 and circle 3, meanwhile, are colored with color 2 and color 3. More generally, the intersection between circle I and circle J, one intersection point is color I, the other intersection point is color J. Does this make sense? Can anyone tell me why this will imply that all of the colors are there on the circle? So for circle I, is the color I going to be on the circle? So if we have circle C, I, is the color I going to be on the circle?
Yes, I will appear n minus 1 times,
And minus
and
one times. So there'll be
the
color.
remaining n minus 1 colors will
Yeah.
appear once each.
Once each. Yes, that's precisely the point. So each color occurs whenever Ci intersects with Cj. So one of those intersection points will have color J, and the ith color will occur n minus times at one of the intersection points between Ci and each of these Cjs. So this is the construction for k equal to n. So yeah, effectively this is the construction when you have that for 3 circles. Does this make sense?
Yes.
Yeah, okay. Okay. Aditya, do you want to explain what you were doing for k plus 1 to n plus 1, by the way? Because your proof is pretty close with the k plus 1 to n plus 1.
Okay, yeah. So I am not yet. I still haven't found the mistake, but basically, if there are suppose case there's a setup for k and n. So consider like any circle and its intersection points with remaining n minus one circles. Since each other circle
So
will
say
intersect
that you
that
have
circle at yeah.
so say that you have three circles initially. So we are now adding a fourth circle, which intersects with all of the previous three circles. So the circle doesn't look very circle-like, but we pretend it's a circle. So each of these circles it intersects. So this is 1, 3, 4, 5, and 6 intersection points. So we just label them 1, 2.
So now that we've drawn the new circle, the circle will intersect the remaining three circles at two distinct new points for every other circle. And so consider the same color in k comma n for the three circle case. And now since we have an extra color, like suppose, which is the n plus one color, and we want to show that there are k plus one distinct colors that we can use. Uh, if we color, I guess, one, so one, uh, uh, so there will be how many? So 2 times n, so 2n. So color, I guess I and 2n minus I is the same color. I'm guessing. So I'm not sure. Uh, that's the point. That's the point. Basically, color the new intersection colors in some arrangement of n plus one, and
You're just
I,
coloring all
I
of them with n plus 1.
yeah, I
So
think yeah, that's what I meant to say. Yeah.
so the only issue with that is that the new circle no longer satisfies the old properties. So
Yeah. So I
remember when
guess
I
we can.
stated this? Yeah. So I guess I'll give a hint here. So remember when I stated this? Assume circle I. Circle I has color I on it. Has color I on it. So assume that circle I has color I on it. Um, so what additional leverage does this give us? So remember you have two intersection points with every circle. So even if one of them is colored with the color n plus 1, the whole circle has gotten the color n plus 1. So the
So
other point we, yeah.
So I think maybe we can color every one point of the pair of intersection points as with n plus one color, and leave the other point as the like the color of the circle that it's intersecting with. Like for example, if the
Okay,
fourth circle is intersecting with yeah,
so you want to color this. So if this is circle 1, then you want to color this
yeah,
point 1. Okay, now
yeah,
this
just one.
is now you have too many
Yeah.
colors on circle 4 because now you have all n colors on circle 4 instead of just k plus 1. So can you find a balance?
See, no,
Uh, are the others understanding this? What's happening right now? Before we go on more into this, because this is the important, it's like the tricky, hard part of the problem.
so I
How do
think
you
this
move
is
from?
I think this is like equivalent to showing that the bound for k between like one and n, so, which is the same thing as we did before.
Uh, k equal to 1 to n is not true, by the way, because every
Okay,
color
okay,
has
then
to appear.
I guess there might be a mistake.
Yeah, so that will be mainly on the base cases. So you will actually just show that some base cases don't exist. In fact, if you want, the idea is k greater than or equal to 3 less than equal to n uh, for all n, and 2 comma 2, that's k equal to 2, n equal to 2, and you have 3 comma 2, this is where this is n, this is k, and you have, so this is the entire family of solutions. Uh, So another tricky part is showing that k equal to 2 does not work for n greater than equal to 4. Yeah, so I'll leave those as exercises. But do want to do this bit where you're moving from k comma n to k plus 1 comma n plus 1. The rest is all just base case stuff. So is everyone understanding what we're trying to do at least? Does everyone understand that?
Yes.
Can you explain how we did k greater than equal to 3? How did we make this bound?
Okay, so I'm not going to go into that. This is like the final answer for people who won't like do it themselves and
Oh,
verify.
all
So
right, all right.
this is just final answer. So currently, all we're trying to do is we're not going to worry about the base cases. What we want is this sort of nice induction leap where we go from k comma n to k plus 1 comma n plus 1. This is what we're doing. So like ignore this. Ignore for now. For now. Yeah. So we'll be
So the
going. So
final answer is 2, 2 and 3, 2.
2 2 3 2 and k for all n you have k greater than equal to 3 less than equal to n. So you have these solutions and this is for k equal to 2. K equal to 2 only works for these two specific values of n. And k equal to 1 doesn't work anywhere. If you have an idea, by the way, speak out, by the way, because like, oh, also, since we're about time, those of you who are busy, don't want to stay, can leave, by the way. We'll just quickly wrap up the induction for this one, and I'll just take any doubts and we can end class. But if you have ideas, feel free to share. But before that, don't ensure. Does everyone understand that we want to go for what the idea for, or how do you want to think about going from k comma n to k plus 1 comma n plus 1, as Aditya had mentioned? Where we're adding this new n plus 1 circle, and we want to figure out what will be nice ways to color each of these points.
Yeah, I think it is understandable. But one thing I want to say, we had already proved that k comma k works, but you hadn't write that on the final answer.
That's the k less than equal to n, right? So this will imply that k equal to n. So n comma n
Okay,
is
yeah.
included. That's this equality bound here. Um, did people understand why we're adding this n plus 1th circle here and what we're trying to do with the intersection points? Feel free to like speak up or like even send a message at least. Okay.
So I have a
Yeah.
doubt. So basically, since we're drawing a new circle and it's going to intersect at two new points for every other circle, and since the other circles would have already been satisfying the k comma n coloring that we assumed in the inductive step, the two new points should be colored with a new color, right? Because if they were to be colored with a color that already exists, then that would
Not
or
change.
yeah, exactly. So. Uh, or I guess suppose yeah, okay, I
One,
have no
but
idea.
just one
Yeah,
point could be colored with the new color, and the other point could be an old color.
yeah. So maybe suppose the case in which k is actually less than n, and suppose in like the circle CI the color J has not been used yet. So then what we can do is you can color the new two new intersection point with the n+1 color and like any j color, like which has not been used yet, and then repeat for the other circuits. Maybe I'm not sure.
Yeah, I see what you're saying. Yeah, that probably would work. The only thing is that you want to ensure that the new circle that you're adding. Okay, sure. Let's go with that, right? So you basically want to ensure that this new circle you're adding has only k plus one distinct colors on it, and you kind of the only issue with the argument that you're giving is that it becomes very hard to control what j it is on each circle. So, for example, if k was like just n minus 1, right, and you'll be continuing with n plus n comma n plus 1, uh, the only issue there is that the color that is missing on almost every circle except perhaps two could be this color I. So that forces I on each of those. So you'll end up with only three colors on the new circle that you've added. That's the only issue with the approach that you gave. Like
Okay,
you
okay,
need to
yeah,
be stricter on the restraint. So not to spend too much time on it, the idea goes like this. It's very similar to the first idea, which is that you color the first intersection point n plus 1 color. Okay, so the circle n plus 1 has color n plus 1 on it. In fact, it has the color n plus 1 on it n times. Uh, for circle 1 to circle k, you give it the color I. So circle I less than k great less than equal to so less than k less than equal to k greater than equal to 1. You give that intersection point the ith color. Okay, the second intersection point. This is because we assume that circle I has color I on it. Okay, so we are ensuring that our circle n plus 1 has color n plus 1 on it. Uh, circle I has the ith color on it, so that doesn't add any color to the ith circle, but it does add colors to the n plus 1 circle for all I greater than k less than equal to n greater than k less than equal to n. The second intersection point is again colored n plus 1. So this does not add any color to the n plus 1 circle. This does not add any color to the uh, ith circle in this because we have colored the first intersection point k plus 1 already with all of the circles. Does this make sense?
yeah, it's clear.
What about others?
Could you please repeat the last part? Like what did we do right now?
Yeah, sure. Yeah, so I split it to two cases. So we have our circles are numbered C1 to Cn, right? Discluding the n plus 1th circle, right?
Yes.
And I'm assuming that the ith circle has color I on it. Okay,
Yes.
and I'm okay. So that means that I have to ensure that I claim that I can have n k plus 1 comma n plus 1, and the n plus 1th circle also has color n plus 1 on it. Okay, so what I do for that is I add my n plus 1th circle. So that's going to intersect at each of these other n circles at 2 points. So the first intersection point with each of those old circles, I color n plus 1. Okay, so the n plus
Yes.
1 circle has n plus 1 on it. All the points except all the circles except the n plus 1th circle now have k plus 1 colors on it.
Oh, yes.
Okay, now the circles 1 until k, I give the intersection point of n, the circle n, and circle what is it? I. So circle n plus 1 and circle I. Their second intersection point, I give it the color I. But this is only for k circles. So circle n n plus 1 gains k colors along with n plus 1. So it now has a total of k plus 1 colors. For circles k plus 1 until n, I color the second intersection point n plus 1 again. So for circles 1 to k, it's gotten the color n plus 1, and it's also gotten a color I, which it previously had. So it's
Okay.
gone up to k plus 1. So there are k plus 1 distinct colors on it. For circles k until n, it's just gotten a new color n plus 1. So it's just gone to k plus 1, comma, n again, n plus 1 again. For the n plus 1th circle that we added, it has the color n plus 1 on it, and it has 1 until k on it. So it has a total of k plus 1, comma, n plus 1, k plus 1 colors on it. So every circle has k plus 1 distinct colors on it, as we want it. Does this make sense?
Yes, understood.
Nice. So that finishes the induction step. So I would recommend, it's not easy, so I'd recommend trying out showing that. Let me just move down. Yeah, I'd recommend showing that for all n, k equal to 3 is valid. So this is actually going to be a base case. It's not an individual case. In fact, it's a whole family of cases. For all n, k equal to 3 is valid. And so for all n greater than 4, k equal to 2 is invalid. So I'll leave this as probably homework, or I'll mark this as part of problem set. Both of these are not extremely difficult, but they're also difficult. They're also like slightly difficult. For problem source, because like I got like 3 messages back to back for that. I think it's like 2004 or 2005 C2. It's either C1 or C2. It's been a while since I've done this problem. 2004 C2, if I remember correctly. I'm a shortlist. So this one's a pretty tough problem, but it's also one of my favorite problems, mainly because it uses like very nice ideas. And yeah, just felt like this is a very sort of unique idea. So working with multiple variables during induction. That pops up fairly often, and it's a very powerful technique. So very often just doing that like kills almost 75% of the problem, figuring out that this sort of jump from k to n, k comma n to k plus 1 comma n plus 1. Does anyone have any doubts? Because this one's not an easy problem. Just about the induction step. So what's with the word game question? Oh, the word game question was some weird obscure source. I think it was some all Russia competition. So it's quite difficult. I personally didn't get it the first time I tried it. So which is why I gave it as like a bonus question for like people who are like really familiar with induction and all, and who are going to be bored in this class, because a lot of the induction we're doing are quite easy. Those of you who want to try it out, I probably won't put this in the problem set because it's too difficult. Those of you who want to try it out can just take a screenshot. Other than that, this class is over. I think you can stop recording now as well.